All right, today we're going to talk about one of my favorite tools in machine learning, the confusion matrix. And trust me, it's way less confusing than it sounds. It's basically the secret weapon for understanding how any classification model is really doing its job. So let me ask you something. You've just trained a brand new model and you check the results. Bam, 96% accuracy. That feels great, right? That's an A grade. But is it really good enough? What if that shiny number is actually hiding a huge problem? To really get why, I want you to picture something with me. Imagine we have this super high-tech factory. On a conveyor belt, we've got a mix of blue spheres and red cubes. In our model, it's a sleek, fast robotic arm, and its only job is to pick out the blue spheres. At first glance, it looks like it's doing a fantastic job, but it has a hidden flaw. Let's put this in a more serious context. Imagine a test for a rare virus. Out of 1,000 people, maybe only 10 are actually sick. Now, a lazy model could just play the odds and predict healthy for every single person. Technically, it would be 99% accurate, but it would have missed every single person who was actually sick, making it totally, completely useless. See? This is exactly why a single accuracy score can be so misleading. We need a better tool. We need a performance dashboard for our robot arm, one that doesn't just tell us if it's right, but shows us exactly how it's right, and, even more importantly, how it's wrong. And that dashboard, well, that's the confusion matrix. It's just a simple way of breaking down every single prediction our robot makes into one of 4 possible outcomes. This is how we get the real story. First up, the best case scenario, a true positive. This is a perfect success. A blue sphere comes down the line, a robot sees it, correctly identifies it, and swoops in to place it in the blue bin. That's a point for us. A correct positive prediction. Next, we've got the true negative. This is also a perfect success. A red cube comes along and the robot correctly identifies that it's not a blue sphere and just lets it pass by into the red bin. Another win. It correctly rejected the thing it wasn't looking for. Okay, now for the mistakes. First, we have the false positive. This is also called a type 1 error. This happens when our robot gets a little overeager. It sees a red cube, but mistakenly thinks it's a blue sphere and puts it in the blue bin. Oops, it predicted positive, but it was wrong. And the other kind of mistake is the false negative, or a type 2 error. In this case, a blue sphere comes right down the conveyor belt, but our robot is asleep at the wheel and completely misses it. It just lets it slide on by into the red bin. It predicted negative, that there was no blue sphere, but it was wrong. It missed one. So when you take these 4 outcomes, the 2 wins and the 2 types of mistakes, you can organize them into this really simple 2x2 grid. This is it. This is the confusion matrix. It's our dashboard giving us a complete, at-a-glance summary of our robot's performance. Now, once we have this dashboard, we can start calculating some much more powerful metrics. These allow us to tune our robot for different kinds of jobs, because you're about to see that not all mistakes are created equal. The 2 big ones are called precision and recall. Think of them as asking 2 very different questions. Precision asks, of all the things you put in the blue bin, how many of them were actually blue spheres? It's all about quality, about not putting the wrong stuff in the bin, minimizing those false positives. Recall, on the other hand, asks a different question. Of all the blue spheres that came down the entire conveyor belt, how many did you actually manage to catch? This one is all about quantity, about not missing anything you were supposed to find, minimizing those false negatives. And this difference is absolutely critical in the real world. Think about medical testing again. You want high recall. You would much rather have a test raise a false alarm on a healthy person, that's a false positive, than have it miss a sick person and tell them they're fine. A false negative there could be catastrophic. And that leads us to the central tension of all of this. You almost never get perfect precision and perfect recall. They're usually in a tug of war with each other. You have to decide which one is more important for your problem, which mistake is more costly. So for example, think about your email spam filter. What's the absolute worst thing it can do? It's putting a super important email, like a job offer, into the spam folder. That's a false positive. So for a spam filter, you'd want to tune it for extremely high precision. You want it to be very, very sure something is spam before it touches it. Now, let's flip that completely. Medical screening. As we just said, the worst mistake here is telling a sick patient that they're healthy. That's a false negative. Here, the consequences are enormous. So you tune the model for the exact opposite. You want the highest possible recall.
You see the pattern here, right? It's a balancing act. If you tell your robot to be more careful to increase precision, it's going to hesitate more and probably miss a few blue spheres, which lowers its recall. If you tell it to be more aggressive to catch everything for high recall, it's bound to accidentally grab a few red cubes, which lowers its precision.
So that raises a pretty obvious question. What if both types of mistakes are bad? What if you can't just pick one to focus on and you really need a good balance between the two? Well, for that, we need a single score that can kind of summarize this whole trade-off. And that's where the F1 score comes in. All you need to know is that it's a clever way of combining both precision and recall into a single number. The F1 score is at its best when precision and recall are balanced. It's a great go-to metric when both types of errors matter. So I want to leave you with this final thought. The next time you build a model or you're looking at someone else's, don't just stop at the accuracy score. Go deeper. Ask yourself this one critical question. For this specific problem, which mistake, a false positive or a false negative, is the one we simply cannot afford to make? Because your answer to that question will tell you everything you need to know.